Welcome back to this tutorial about dynamic simulation. In this case, we have a very simple sample of one pulley and two masses. So this example comes from, it's something that I found on the internet. This website Structure Independent Learning, that's totally fine. So they have a pulley, two masses, one of 30 kilograms and the other one of 20 kilograms. And the thing is to find the acceleration at the moment of releasing the masses and also the tension. So uh, let me show you very quickly where we are looking at these results and how we can just verify that we're getting the right answer, right? And then later, after that, I show you guys how to set up this thing. Okay, so there you go. Perfect. Okay, so I just want to highlight the two results that are telling me that this is totally fine. So if I expand this, I will see that the force is expressed in newtons and this one as well. And the acceleration is, well, there you go, millimeters second square. Okay, let me do some annotations in here. So these two forces are the tensions coming from the rolling cylinder on plane that we are going to take a look in a bit how to set up. So we have the force on both. Both are 236. They're not exactly the same because the masses are not precisely perfect 20 kilograms and 30 kilograms. But anyhow, this is very, very accurate. So we have the result from the exercise about the tension. So tension is matching 235 newtons. And talking about the acceleration, in here is in millimeter second square. Here is in meter second square. But anyhow, this is totally fine. I mean, it is 1.96. Here's 1.95. So yeah. Okay. So now that we have verified that all these matches and this makes sense, let's make a quick view how this thing is set up. Okay. So returning here, I will double click in here. I want to expand this thing. Okay, there you go. All right, perfect. So as mentioned before, I have, I don't know why this thing's grayed out in here. Okay, so my setup is very simple. I have a fixed part that is having this hole. Remember, these things are simplified in the model, but we can go with more detail, but in this case, it doesn't work. I would say this is something that you can do on an early design state for prototyping, so you can make sure that the 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 mechanism is working as expected before and starting to work on details and stuff like adding bearings, defining shafts, and all that. Actually, you can take the data from the simulation and let that data or those results to drive your next design steps. Okay, so I have this thing fixed. I have this wheel that I put some circles so we can see it rotating. If not, okay, so, and it is floating in this direction. This is because when we enter into the dynamic simulation environment, dynamic simulation takes the current mates that this part has and convert them into actual joints inside the environment. So for a reason that I'm not sure, taking an insert in between this hole and this plate creates this plate as a rigid component, and I don't want it to be. I wanted it to rotate. And if I take an axis, let's say a regular constraint like this, with the two axes combined with the face-to-face, let's say a mate, also create that effect. So I'm having it floating, but you will see in a bit how to work with that situation. Okay, and then I have the masses. One has been set up as copper, the other one is set up as stainless steel. And I did the calculation for half their masses very accurate. So if I go into iProperties on the physical properties tab, you will see that this one is 30.080 kilograms. And if we go into this other one, physical, we got 20 kilograms. So we are down there. Okay, so as you already saw on my left side, I have some mates that are suppressed, and this is as simple as just for the setup, initial setup, I like some mates to help me to have the parts where I want them to be. And then I suppress those mates because they cannot be active when we jump into dynamic simulation, because if not, everything is going to be rigid. Simple as that. Okay. Now we have just explored how the model looks. Now let's jump into the environment of dynamic simulation. Okay, cool. So I wonder why this thing is grayed out. Let me stop in here, take this. There you go. Now it is not anymore. Let me finish dynamic simulation. Oh, now it is not grayed out. Cool. All right. Sorry. Okay. Don't forget to subscribe. Now let's get back into dynamic simulation. We have our simulation player, which is something that if you have seen other previous videos from me on dynamic simulation, this is a really common thing. If for a reason you close it, you can turn it back, take it back with this button right in here, simulation player. All right. So as mentioned, you will see that we have a group of parts. We have grounded parts, which is the rectangle at the back that's expected. We have this wheel. We have the mass of 30 kilograms and the mass of 20 kilograms. So Autodesk Inventor took the mates, the existing mates of the things. Well, these ones are suppressed, but it took the mates and created these standard joints. So as you can see, those standard joints are coming with something, right? With a mate. Okay. So going down on this tree at the left, we can see that there are some joints that are called rolling joints. So this is where the magic happens. There is a reason why I have this axis turned on both of the masses. So it doesn't matter if the geometry is a square or something prismatic different from a cylinder. As long as we have this axis, that's going to work perfectly fine with the rolling thing. So let's go into the insert joint. And as you can see, we have here plenty of options, but one quick way to get it is by clicking in these squares. So we are getting in here is a list, the same list of things that we can do, but on a more graphical way. So right now, what we're looking is for rolling cylinder, well, let's say rolling joints, because in reality, we want a rolling joint. And we're going to look for a cylinder on plane. So after clicking here, you just click here. Okay, that's totally fine. And now you define the thing. So as you can see, we have, let's say, two sections here below. We have the plane that can be a plane or an axis, like our case, and the cylinder. So I know that this representation seems to be like a rack and pinion, but it also applies to here. And you already saw the results. So it works as a pulley, really. So the axis, of course, is going to be one of the axes of our masses. You can jump, you can leave this thing in here. This is like more like define the origin and the orientation of the triad for it, but that's more useful, or that has the intention of controlling from which point you're receiving the data on the output grapher, which is the table with the graph that I showed at the beginning. So it is not that important. Let's leave it like that. And now let's click on the cylinder. So I click on the cylinder and it's the same thing. I'm pretty sure if I click in here, it's going to tell me that it already exists. There you go. Oh no, it is an over-constrained by 2 degrees. Okay, so let's delete this one. Okay, so that's how I did the setup for these two rolling joints cylinder on plane. It's simple as that. I'm also including a couple of 3D contacts because I was playing around with this, and I put two 3D contacts in between the pulley and the masses. So if they get in touch, they are going to interact. Of course, the gravity, very important. Without the gravity, this thing cannot move. So as you can see, the gravity is set up, and I included force that I was playing with. But yeah, I think I'm going to delete it. All right. Let me, okay, clicking here. It was a time-dependent force. I can explain this, of course, as well. Okay. So how does it works? So I'm applying the force at the end of at this point, right? So the location, and the location I was picking this point, or this edge of the cylinder. And I ask for associative low direction. So that means that if this thing is moving, let's say, like pivoting, not staying perpendicular to the gravity, or parallel to the gravity in reality, it is going to change. It is going to follow the direction of the vector of the reference. Okay. So in here you have two options. Once it's constant value, so you apply there a value that is going to be constant all over the time of simulation. The other one is use an input grapher. So with the input grapher, you can control at which time the force appears and at what time it ends, let's say. You can select, let's say 1 Newton, for example, in here, and we are going to have slope. So in my case, I was more interested to see what happens if I apply a load for counterbalance the thing. So let's make this more interesting. So I will say that at 5 seconds, which is a lot in reality, our simulation takes just 1 second. It's extremely fast, this thing. So let's say that at 0.5 seconds and up to 1 second, let's say 1.5 seconds. It applies, let's say, a load from 0.5 to up to 0.7 newtons. So as you can see now, we have a slope, and something important to highlight in here is that at the left, it is free, but you have options for apply different conditions. So let's say I will select here at the left. So I'm going to control this area here. So I can say, okay, now let's go constant value, for example, constant slope, module, and also free. So I'm leaving it as free because it sounds like more interesting to me. And at the right side as well, I will leave it on free. So it's just a little bit. All right, let's click here. Okay, let's add here a couple of, I don't know, 3 seconds. It's going to be okay. And so they're starting from at the same level, let's say. So I will, just for the sake of making sure that everything is going to run okay, I will click here on rebuild all, jump again into the dynamic tab, and I'm going to hit run. So as you can see, it is moving, it is making contact, it is kind of returning. All right, so let's see. So the force is being applied in this direction, but doesn't seem like it's making a lot. So let's make a quick change in here. I will change definitely the location of the load to this other one. So now we can have something that's going to go the opposite direction. Okay, so once again, go to manage, rebuild. It doesn't hurt. Okay, let's go. So at 0.5, there should be a force. Ooh, it seems like it's not enough. I wonder why it is not really making a difference. So let's go on 100 newtons. So it's a lot, actually. Rebuild all. Let's click on save. Let's click play. There you go. Now it is having effect. There you go. Whoop, just a bit, yeah. 100 newtons makes sense. The difference in between them are 10 kilograms multiplied by 9.8. So yeah, it was about 100 kilograms. That makes total sense. Let's add the next level of complexity, which is adding the friction at the wheel. So this type of exercise usually are under perfect condition of no friction at the wheel, but real life is different, right? So let me just highlight something that I have not mentioned. That is that we have on the properties of each joint, we have the different degrees of freedom. So this wheel is having one translation and one rotation. So you can see the T for translation, you can see the R for rotation. So actually the translation is lock. That's something that I already did when I was preparing the exercise. About this rotation thing, it is not lock. This is actually the initial condition. Now I'm going to jump into the joint torque, and I will click in this enable joint torque, and I will use a coefficient of 0.1 and a radius, this is super important, of 17 millimeters, which is the radius of this thing. So this is kind of assuming that we have a shaft there. So that makes it more valid. Okay, so we have a a friction in between the shaft and a push-in or something. 0.1 sounds like a little bit high, to be honest. And I will go to manage, rebuild all, don't forget, and let's click OK. So the thing is probably going to move slower because of the friction. So let's see. There you go. It's moving back. It's returning. So as you can see, it is um, making a movement there, like pivoting thing. Okay, there you go. Now let's take a look to the results on the graphics, on the output grapher. So we have our newtons. As you can see, the first second, or let's say the first time step, it is exactly the same thing that we saw before, 236, and the acceleration 1.9 meter second square. But after that, it starts to change. Well, it changed dramatically. It makes a jump because of the friction. There are friction, there are losses. As you can see, it is flat till 0.5 seconds. Then we have in action our extra force of 120 newtons that is pulling down. We have their constant values, and then it returns and makes contact, and that's a different story. That's a more dynamic thing. So this is just for 1 second, we have a very high force in there. So in order to look for that max force, if it is important, it is basically a chalk, right? So you can right click here at the top of your column and click on search max. So there you go. There is our max in this point. And that makes total sense because it's the first time it touches. But yeah, it makes contact, sorry. So, so how do we get all that thing, right? So there are many ways. There are like 3 ways to get these results. One is by just opening these things, right, and clicking on the different options. So, but you need to know what are you looking at when you click force. So how could we know what we're looking at this moment, right? So the answer is simple. When you go into, well, you need to come back to the initial state. Then you go to the rolling, for example, the rolling on plane, double click it. You can turn on this display. So I would click in here. I will double click this one and click in here. So now when I click OK, click play, I will see that these arrows, those arrows are the forces, the representation of the forces. So as you can see, so direction changes and all that. So that's the force that you are looking. If you have doubts about it, just go and turn on that option. So now you can know what exactly you're looking. So it is great because we were expecting to have pulley simulation, and the force is a tangential force. So there you go. It is tangent. Okay, very good. So I hope you have found this simulation useful. Don't forget to subscribe, and also if you want to give me a like on this video, I really appreciate it. So just one final thing here. If what happens if I do it like this way? Okay, cool. It's having fun. So remember, all these simulations are simple, but they are the basis or the basic base that you need to know for make more complex things in your simulations. Take care. Have a nice one. And well, actually, if you're still there, you can click in this other video. I'm pretty sure you're going to like it. Cheers.